Good afternoon, everybody. This is Ken Biba, your presenter, and thanks for attending. I'm going to wait a minute or so to see if let people join in before I start. And bit of housekeeping stuff. We're still learning. I'm still learning a bit about the Excel events platform, so I'm not exactly sure whether I'll be able to do Q&A during the session. So if I don't, I'll try to come to. My intention is to stop a few minutes early and do Q&A at the end. Secondly, I have embedded video, and we think it works, but quality is I'm not going to go testify to it. So we'll see how well the quality works on the video. And that's probably as much as I know. So I'm going to give it one more minute. And then I'm going to get started. And hopefully everybody can hear me. And if so, I'm going to start going. So welcome to the session talking about ARLISS. It's the acronym for a rocket launch for international student satellites. And aside from last year in COVID madness, we've done 22 years of rockets, robots, and STEM. It's the original we invented with Bob Twiggs and his colleagues, CanSats and really CubeSats. And I want to think about a theme as we go through this today, which is that we have started with a project that was for very elite aerospace students of high-end aerospace universities. And hopefully we're moving to something where CanSats, CubeSats, and now PocketQubes not only go through many, many universities, but also down to the high school level and kind of as an advanced TARC project. And I'd like to be able to introduce some of the projects we've been working at. One of my themes today is to kind of, for those of you who haven't been part of ARLISS, is to kind of refresh all the projects we've been working on. You'll see a wide range of things that the members of the ARLISS team have been working on. And I'll try to start a little bit of the history, and we'll kind of move towards what we've been doing over the last 20 years. So just to refresh, you guys haven't met me. It's a better picture of me a few years ago, looking really good out on Black Rock. I originally wanted to be an astronaut, and many of us who grew up in the 50s and 60s wanted to be that. But as we remember, you really need to be a fighter pilot to be an astronaut, and I was not a good hand-eye coordination guy, and that was not for me. So instead, I needed to go discover robots that needed to explore for me. I ended up being a physicist, a computer scientist, an entrepreneur, built companies, took them public. I'm my particular skill set is a wireless network expert. I've actually got a satellite in orbit that sent packets down using $5 radios. And I've done 30 years in amateur rocketry as a ham, a TRA level 3 and a TAP, member of various boards, held amateur rocketry records, altitude records, got my own satellite in orbit, and I'm now passionate about using rockets and satellites as a vehicle for exciting students of all ages about STEM. So how did ARLISS begin? It was trying to address the problem of how do you develop engineering training for space? And it's a long development cycle. It's a long time to put your own satellite in orbit. It's really hard to build rockets that go to orbit. And it was then 20 years ago. And to today, while it's getting better, it's still hard. Space is hard. So, and then the second part is most engineers build payloads rather than rockets. It's far more interesting building, in some ways, more interesting to build satellites. So ARLISS, unlike some other programs, focuses the training on building great payloads and not just on rockets. The second was inventing new standards for payloads, and the CubeSat directly comes out of ARLISS work, and now moving toward what we call PocketQubes, which are essentially half the linear diameter, or it's 1/8 the volume of a CubeSat. And PocketQubes are interesting because they essentially are smaller than CanSats. They can fly in little park rockets to 1,000 feet, or they can fly to orbit. And because they're smaller and lighter, they're cheaper, both on things we do on the ground and things we do in orbit. Second piece is LEO is a relatively benign space place, being inside the Van Allen belt. So commercial electronics work pretty well for reasonable amounts of time. So things we build in small satellites here on Earth work pretty well in low Earth orbit. And the idea was to train for space closer to ground. So we now have a 20+ year history. It was the original CanSat program. Linking to a talk recently that Bob Twiggs gave. Bob is the founder of our feast, and in 1998, he hosted a conference in Hawaii, meeting with some colleagues from the University of Tokyo to invent CanSats. And then he recruited us guys from AeroPac. In 1999, we held the first CanSat launch at AeroPac. It was the first ARLISS launch. And two of our leaders of AeroPac at that time was Pius Morozumi and Tom Rouse. Tom is still with us, and essentially created a unique partnership. So the idea was students focus on building payloads, and we get some experienced amateurs to build rockets and fly them. And this is much like what we do as professional engineers building satellites. Very rarely does one team build both the rocket and the payload. Instead, you build a payload and then contract with basically a bus driver to put you into. So today, it still goes on. It's hosted by us, AeroPac, every year in September, and it's organized jointly with UNISEC Global, a worldwide university space engineering consortium. And particularly, what you find at ARLISS is a lot of engineers get trained that build the first satellites for their countries. ARLISS is now both a TRA activity and a NAR section, and we get students from all over the world. My favorite story is about, many favorite stories, but one of them, we had a team from Egypt that was building a robot. We'll talk more about how it gets deployed. So they could only test it at night in parking lots because they were afraid that if they did it during the day, they would get caught by the secret police and arrested. So we have very passionate developers that will do great things to create stuff. We've now flown over 700 missions, and one of our great moments of pride is we've only had 3 failures to deliver that payload and deploy it. So that's a pretty great mission success ratio. And we now have thousands of students have passed through the program. So, and hundreds of SATs actually. So I want to point to some of those alumni. One of the first ones is Dr. Tsuda. He's now at JAXA. He was literally at that 1998 meeting as a graduate student with Bob Twiggs, and they invented CanSats there. He then went back to his university and built the first CanSat deployed, which we flew in 1999. He went on to then at the University of Tokyo build the first CubeSat and take it into orbit. And his most recent adventure, he was the project manager for JAXA's Hayabusa 2 that went to an asteroid and returned a sample back and recently returned it successfully. So one of the great successes of ARLISS is providing an experience that works for this. I made a link on the bottom to his particular talk that talks about a little about the history of ARLISS, but also talks about his experience about how this education process works. So over the 20 years, we've done a bunch of ARLISS projects. The core of it is something I'm calling ARLISS Classic, which is we started with each airframe was a 6-inch airframe flying on an M1419 with 3 soda can size CanSats. That was the 1999 mission. That has now moved over the 20 years that now those things are really autonomous drones. And for the last 15 years, We've been flying basically 1 kilogram drones to 10K feet and throwing them out, and they have to return. We'll talk more about that. The second piece, sponsored by Bob Twiggs, that we did was create something called the Virtual Classroom, which was essentially creating an internet out on the Black Rock Playa to essentially do streaming services like we're doing here to essentially the entire world, and particularly to the third world for many of our students. We did that from roughly 2006 to 2015. We then instrumented deployment. So the model that Bob had for ARLISS was that we were emulating a typical orbital mission. We'd have roughly the same G load going up. We'd have roughly the same shock of deployment. We'd have roughly the same time in the air as it took for a low Earth orbit satellite to go past horizon. But every one of those commercial launches knew exactly what the deployment environment was. So we decided to instrument a payload system to essentially measure that for ourselves. Being ambitious, we decided to go from 10K to 150K, and we invented ARLISS EXtreme and ARLISS towards the Kármán line in 2012. Our first one of those missions set the new amateur record at that time of 104,000 feet totally recovered. We then dropped the size of ARLISS payloads with something called S4, which was a NASA-sponsored program, to essentially create PocketQubes as the new CanSat. We'll talk more about that. And lastly, once you have small satellites, you can begin to fly them not just to Black Rock Desert or other places on HPR motors. You can fly them on E, F, and G motors in your local park. And we'll talk about that. ARLISS Classic. The model was we have very experienced amateurs fly reliable HPR K&M powered payload rockets with student satellites. Standard payload was either 350 grams for the K rockets or a kilogram for the M motors, and with a standard flight acceleration and shock profile. The model of flight, we fly up to, whatever it is, there's variation based on weather and the particular airframe, to 10 and 12,000 feet. You separate at apogee, you have a little bit of a deployment model, and you have a carrier deployment of the payloads that will then come down as they will. These are now really evolved, and almost all of them are student autonomous satellites that find their way back. They're given a predefined set of GPS coordinates on the Black Rock Desert, and they pick their own way to come back. The winners are very simple, the closest to the goal. And in memory of our partnership with our Japanese teams, it's generally a Japanese flag there. And the closest to the goal wins. And you can, as long as you're within the volume and weight constraints. They can fly, call, or glide. And over the years, the portfolio of how many payloads fly, call, or glide has changed. I list you a couple ones describing some of the historical documents. And in the lower left, you see a typical ARLISS M rocket. We try to use the same basic plan form for every ARLISS. And we use the same motor, which is largely an M1419. And we try to have the same flight profile for every student. So they're all flying with a common background. So ARLISS satellites have gone from a simple CanSat. This is like a legacy one. You can see it's kind of a old construction, to CubeSats, this is one of my favorite ones recent years. This is probably maybe 6 years old. So this has retractable legs that fold back for deployment, and they get expanded when it gets deployed. It comes down on a parachute. And when it lands, because these are very, very, very great on traction on the desert, this is an all-terrain vehicle. This did very well in the competition. And then recently you can find PocketQubes. Now these are 50 millimeter cubes on the left, and then you see a 2P, which is 100 by 50, and then a 3P, which is 150 by 3. And then this is a more modern one, a version of that happens to be with antennas for telemetry. Let me see if hopefully this video comes across. This is a video of the entire mission. I have to say I love the M1419. It just has such a great sound. So this came down on a parachute. You can see it has landed. The team can't touch it. Yeah, all they can do is watch it. And so we see this little satellite struggling to get itself out of its packaging. You can almost see it thinking. And right now the team is freaking out because they think it's never going to get free. This was a Japanese team. Oh, now they're freaking out. They'll get caught in the parachute. Nope. So it's now figured out which way is towards the goal. And now it's doing an autonomous goal seeking. This team went out and followed their satellite home. Now, this one landed particularly close. You can see the base. But some of these have come back from as far as 4 or 5 kilometers away. The fastest I'm aware of came back at 40 kilometers an hour. One of the things you obviously can see how this tests. First of all, it's hard to survive the landing. You can see the guy with the flag. He's standing at the exact GPS coordinates. You can see it now, figure it out. It's looking for the goal. So it stopped basically within GPS resolution, which is 3 meters. Now, one of the things I want to point out is that that was taken almost 15 years ago. I think it was 2006 that particular video came from. And the last time we did ARLISS in person, which was 2019, the winner was a woman-led team from Japan. And she in particular was an expert in machine learning. And their particular piece of doing the comeback project was to have multiple cameras and to do machine learning of the path. And they flew their project 3 times over the 3 days of flying. And 2 out of 3 times, their project hit, we had a pole that year holding the flag. 2 out of 3 times they hit the pole. The last time they stopped 2 centimeters away. So I think that's an astonishing set of performance because it's much higher than the resolution of GPS, and do it repeatedly is totally astonishing. So these teams are world-class in terms of their ability to build really amazing things. The idea of CanSats have now deployed across the world. We find many CanSat competitions, but ARLISS is still, to my mind, well, it's definitely the first, and to my mind, still the best. The second project we did was the ARLISS Virtual Classroom. This is Bob's original picture. It's a virtual presence for education tracking voice. You can think about as the first internet ground station website video conferencing. And we did this from 2006 through 2016. We implemented it ultimately in it was a donated TV van, which had a 40-foot mast, which we mounted antennas and cameras on. It had a retractable satellite and cellular internet. We had local servers and Wi-Fi hotspots and a bunch of both UHF and VHF voice and tracking gateways. This was actually the ground station for our 2012 tracking of the 100K flight. I list you a couple of resources to go learn more about it. It has now been retired to be a California emergency services asset. It's used for fire response in SoCal. And largely because we now have at BlackRock cellular service. So people can now roll their own ground stations rather than using this one. Instrument deployment. We want to document the flight stresses on payloads. And so we built one, and it was lit for shock, vibration, and acceleration. And it fits in the bottom of an ARLISS M payload deployer. And it was led by a team of Bob Twiggs and his team from roughly about 2012 to 2017. I think he may still sell this board, mostly because it has a 200G 3D accelerometer, a 2,000 degree per second 3D gyro. Most importantly, it collects data at over a kilohertz, which means we have very detailed data about the experience of flying in an ARLISS rocket. We have great data. Here's an example of looking at the conventional flight acceleration events that you'd see. And now what we discovered is that just simply the acceleration measured by the accelerometer wasn't good enough. So we did essentially a discovery about deployment shock. And so there's a whole analysis about how we convert from simple acceleration to the shock spectrum across a set of frequencies. And you can see the amount of shock you have, peak acceleration, varies a lot across the natural frequency of the shock. Bob and his team wrote 2 great papers. I give you 2 links to the 2 of those to look at that analysis. It turns out we have a whole bunch of data that still needs to be analyzed. I think we have over 100 flights here of really good data about flying reasonably big rockets. Then we got ambitious, and we wanted to essentially do the same model as ARLISS, flying experienced people to the edge of the atmosphere, and reusable. So low cost reusable amateur sounding rocket. This is one version of it. It's a 2-stage, and it was based on a successful 2012 Carmack Prize winning system. You can see myself and 2 of my colleagues, Becky Green, who now sits on our board. That's the actual rocket, and it's in the Seattle Museum of Flight. And the mission is to fly science payloads to 40 to 80 kilometers. And what we find is that at that point, we think we can fly 3 PocketQubes. And it's possible at that altitude, you can begin to do real science when you're above much of the atmosphere. We figured out through many simulations and experience, it's a 2-stage 4-inch to 3-inch airframe. Goal was off-the-shelf parts, commercial rocket motors to be reusable, to fly within NAR and Tripoli rules. And we believe we've done that, fully recovered, reusable. The flight is basically the cost of propellant, much like SpaceX now talks about for both Falcon 9 and for Starship. So the goal is that the motors we use cost propellant is about $1,500. Give you a link to the original program report, which still is really relevant if you're looking to build high-performance 2-stage rockets. We are still debugging this to go to our goal of a fully reusable system. So we're still in the midst of not meeting our goal, but hopefully getting there. Here's a video of that flight, about that. So I still like looking at that, and it was a great accomplishment, and it was great teammates. So let's look at then ARLISS S4, which is small satellites for secondary students, which was conceived by one of our partners at Sonoma State University. And they got a NASA grant to essentially try to downscale ARLISS to work with secondary students, again, focusing on payloads. And now that's progressed. Now we can build those into PocketQubes. And I'm making the argument to you that PocketQubes are the new CanSat. So it's a 3D printed 5 centimeter PocketQube package. You can see an example of it there. Is the baseline. And you can see one of our students from a seminar we did in Chicago, who essentially has just now put it all together. He's 3D printed his own package. He put together and soldered his boards, he downloaded the software, and all of a sudden, it's working for the first time. And he's just built his own satellite. So it's based upon an ARM, 120 megahertz ARM now, with do it in C++ or Python. It has more sensors than I know what to do with. Not only 9 degree of freedom kind of position sensors and GPS, but also things that measure pollution in the atmosphere, ozone sensors, gamma ray spectrometers, particle spectrometers looking for dust particles in the atmosphere and making their size profile. And I run out of, we can now add in LoRa wireless. LoRa, if you don't know, is the new IoT one of the new IoT standards. I've flown a rocket, a payload to orbit, demonstrating that LoRa works from orbit with a $5 chip. It's the core technology you now see in featherweight telemetry. So the key thing is to design a mission for our students. We can design a mission to measure flight dynamics, measure air pollution, measure plant growth by looking at cameras down and looking at false color images. We can measure water coverage in the same way, or we can build a small autonomous robot. So in this small size factor of essentially a 5 centimeter cube, or maybe twice that size, we can essentially build satellites that we can fly in a park locally, we can fly at Black Rock, or in fact, we can fly to Leo. And so what we can build is a range of S4 launchers as hobbyists or as students. So if you have your favorite little PocketQube, you can fly it on an ARLISS Lite to 1,000 feet for $20. You can put it on a classic ARLISS K and fly it to 10,000 feet for $40 a flight. You can fly it on a classic ARLISS M, 12 or 24, kind of depending on the packaging. Fly a whole swarm of them for about $40 a satellite, or fly it to the edge of space on an ARLISS EXtreme for about $500 a flight. And so then you can build your own little rocket. 3D printing has dramatically transformed this. So this is an optimized minimum subsonic drag. Payload is based upon to fly S4 satellites. And I have variants of this that can fly on various different motors, and you can fly 1 to 3 of them. Based on a single fiberglass body tube, this happens to use Altus Metrum avionics. And the rest is 3D printed. The nose cone, payload inside, flyaway launch system, fin cans, recovery anchor, motor retainers. Most of our TARC students can build one of these. And the flyaway system works pretty well. So then you can put it to orbit. So that was a Rocket Labs Electron flying in November 2019, carrying FOSSASat, which was developed by a team of Spanish high school students. It is a 1P PocketQube running an Arduino. And actually, they went to Leo, and they succeeded in demonstrating that same $5 radio that I've talked about can work with telemetry. So they also backed up what I did a bit earlier, but this is done by high school students. So we should think about this as now what we were able to do with students focusing on payloads. So what I'd like to leave you with here and move to questions is that it's all possible. Technology has moved on a lot so that we can build rockets using 3D printing or using what we've learned to run missions from 1,000 feet up to orbit. We can build satellites like we did with ARLISS that allow us to fly not only here on the ground, not only fly on big motors, but on MPR rockets. And we can build all of this, and it's all possible. So I'd like to thank you very much, and I will entertain questions. Oh, so the first question I have is, what is the strangest, funniest we had with ARLISS student teams? Oh my. I gotta think about that. Funniest. I tell you, for many, since it's an international launch, many of our teams, this is the first time they've ever been in the United States. Right? The college students, mostly. And secondly, they come for their first time in the United States. Where do they end up? In Gerlach, basically, and in Blackrock. So their experience in being in the United States is kind of a strange one, right? They fly in probably into San Francisco, they get cars, and they go out to the Black Rock Desert. And so being able to have that experience is probably the most amazing, weird thing. Second piece I'll add to that question, it's a different variation on it. My most satisfying experience, other than flying student payloads, which is frankly one of the most responsible experiences I'll ever have. These kids have worked on these programs probably for a year, and then you have the responsibility for flying it successfully. Let's talk about pressure for a moment. But we hold on a Friday after a week of launches. We hold every team has to make a 5 to 10 minute presentation. That presentation is absolutely amazing. And just standing up, I have some videos of that, which I didn't show here, but I can, that show these students, many of them barely speaking English, being able to stand up and make a cogent presentation about their project, mostly about what failed and what succeeded. It's really a very, very amazing presentation. COVID. We held for AeroPac, we actually had launches last year that were limited in size by Nevada to 50 people. All our student teams canceled because their universities would not let them fly, and in particular, not flying internationally. Right now, our student teams in Japan, internationally, are open. No one's made a decision yet because we're at an amazingly bubble with vaccines. I think it's going to depend on what international travel looks like, and we're probably a couple months away from really answering that question. The audio didn't come through on the video. I will try to post links to the videos. And so let me try to add that, come back in a day or so and look at the documents, and I'll hopefully be able to have something there with the links to the videos. And let's see. Any other questions? Well, you've got me here. What I should add is our partner for the last 20 years has been UNISEC and now UNISEC Global. UNISEC started out as a consortium of Japanese universities, and UNISEC Global is a consortium of worldwide universities. Many of those universities are the first group of people to study aerospace and the first group of people to put up satellites for their countries. So it's a very, very interesting group of universities. And you can look for them on the web, UNISEC Global. PocketQube to orbit. You can buy a ride for a 1P PocketQube now from Alba Orbital. They're selling spots now. It's about $28,000 today. My guess is the cost is going to come down. There's great competition on the cost of this, and Alba Orbital has put together a set of PocketQube deployers, and they then broker selling missions. And so I refer you to their website. We are still flying ARLISS K missions. For ARLISS Classic, the vast majority, I would say, each year we fly about maybe 50 missions at the September launch. Probably 47 out of 50 are all ARLISS M. And I think that will begin to, mostly because everybody's flying autonomous robots, and it's hard to make small autonomous robots. We saw in 2019 launch, we saw some autonomous robots that were very interesting, crawlers, that could essentially fly in, let's call it a 2P PocketQube size. So we'll see. Yes, we're still flying ARLISS K though. There's not a huge demand for them. And thank you, Bill, for the link on YouTube for that. That's the video for the 2012 flight. I look at the audio. I think it's really great. And for those of you, one of our members at that time, and still is, was working for Google. And at that time, Google was giving everybody who worked for Google some set of money because Google had too much money. And that helped fund our project that year. And Google at that time was fascinated with space. And they actually sent a video team out, and that video came from that video team. Before they came out, they actually they bought 4 4K cameras, which in 2012 were, shall we say, leading edge. And the rumor I have is that video cost $500,000 to make and was really designed to be an advertisement for Android. So I really thank Google for making the video, but they were not really the sponsor for the flight. We did it ourselves, and we happened to scam some of their money they gave to one of their employees. They'll pay for it. So thanks, Bill, for the link. And let's see, what else? So each year right now, we're getting about somewhere between 40 to 50 teams. Highly dominated by non-US teams. We get them from all over the world. Probably a third of our non-US teams come out of Japanese universities, as indicated by our Hayabusa 2 project lead. And they're deeply committed to continue this, and you can see they had great success. They actually track, I think the number is something a little over 100 satellites that alumni of ARLISS have put into orbit as part of the project team or as the lead of the project team. And as far as we can tell from our conversation with them, they're going to want to continue this forever. They view this as a very successful project for discovering how to educate new engineers. Gary reminds me to talk about being a requirement. So we always need more ARLISS flyers because many of us are getting old and we need new ones. One of the cool things about being an ARLISS flyer is that you get free motors. So if you come out to the launch and fly these flights, the teams actually pay a small fee. They pay the costs of the motors. And so for the cost of the motors, you get to fly either Ks or Ms. So ARLISS Ks generally fly on a K550, and an ARLISS M generally flies it on M1419. So if you're an ARLISS K flyer, we need you to be an L2, and we need you to show us a demonstration flight that the rocket you've built flies successfully. The same thing is true for ARLISS M. We need you to be an L3 flyer. We need you to demonstrate that you can fly one successfully by flying a demonstration flight. And then after that, we pick up all the motor costs, and we have a modest little pool of money for replacing parts that break. Because rockets are rockets and they break. But that's the core requirement. Be a certified flyer, be willing to spend your time, build a rocket, show us that it works. And we have gotten to a point right now that some of our best, most experienced L3 flyers can fly 3 M flights in a day, which is kind of an amazing kind of number to do. Have it recover and deploy successfully and fly their student payload successfully. So as ARLISS flyers, these are some of their amazing set of, my colleagues are just an amazing set of flyers. Bill, the question, is there a central web location for documentation for ARLISS satellite payload projects, such as circuit design and software? No. We don't standardize that. We don't really control what the payload is. They work on that design with their universities and their professor. Many of them, we never see the documentation. We get some of them. We've asked for their presentations at the Friday seminars, and we get some of that. And I have some of those records that I'd be happy to share. Almost all of that is about the hardware. I don't recall anybody really giving us any information on how the software works, which has been, frankly, pretty disappointing. Actually, that reminds me, though, about one of my favorite projects. One of my favorite projects, now maybe 4 years old. Their project was to build, they built a satellite. It was about the size of a coffee can, 1 kilogram. It landed on a parachute, turned into a rover, two-wheeled rover, but had on its back, it deployed periodically little radio towers across the playa. Those radio towers each had its own little battery and its own little Internet of Things radio. And essentially what it was creating was a little network of radio towers in its path. And its model was trying to emulate what someone might do to create the internet on Mars. And being a radio geek myself, I was really impressed by that. Payloads have changed. Updated designs of payloads or ARLISS rockets. The ARLISS rockets haven't dramatically changed online, but please send me an email. I can kind of give you an update as to what we're looking at, as to what the new standards are. But the new standards for ARLISS payloads are truly amazing. Increasingly, we're seeing use of quadcopters, and payload carriers haven't changed. We still have an inventory of the instrumented payloads, which we use sorta, but they're basically backward compatible for payloads to standard payload carriers. So a standard payload carrier is about a little under 12 inches long, and it's generally a fiberglass coupler with a base. So think about 6-inch fiberglass coupler. That's basically a payload carrier. Okay, we're getting near the end of our program. I'm available via email to any of us, or and we're going to continue doing ARLISS for as long as we have strength, and looks like our colleagues internationally want to keep doing it. One of the things we benefit from being at BlackRock is it's flat, and so we can do these autonomous recovery things in a way that really is not possible in most other launch locations like New Mexico. So we can do recovery, payload recovery in an interesting way. Generally, ARLISS is the week before balls, or 2 weeks actually. So way we have scheduled is there's a AeroPac launch every year called Express, XPRS. XPRS is generally the weekend before balls. And then the week before XPRS is dedicated to ARLISS. Now, one of the cool things if you decide to become an ARLISS flyer is we take the waiver up to 150K now. So while if you go to balls, you may have a day or two of 150K waiver. If you are an ARLISS flyer, you probably have 4 to 5 days of 150K waiver, and no people and no lines. So when we fly ARLISS Express, we take advantage of that by flying during the week when there isn't as much a demand. Okay, folks, I'm gonna count down now, and I'm going to close down the broadcast. Thank you all for your patience, and thank you all for your interest. And please be ARLISS flyers. And also think about, as you mentor people, use the S4 system. You now can take not just coming to Black Rock, but you can fly anywhere and fly a very sophisticated science mission, a very sophisticated payload that is partly 3D printed, partly with leading edge electronics, leading edge sensors, and you can build a small 3D printed rocket that's optimized to fly. Thank you very much, guys, and it was a pleasure letting me talk. I'm going to let you go.